So in this Pencast, we're going to use a Kb value to calculate the pH and percent protonated base in a solution of a base. And the base in this case is actually nicotine, which has the chemical formula C10H14N2. It has a very complicated structure. We're not going to go into that here, but what we need to know is that it's behaving as a base in this problem. And we're given a Kb value. So immediately I should be thinking, okay, what chemical reaction is going to be the appropriate one to use to find the pH and percent protonated base? Whenever we're given a Kb value, that means that it's the base reacting with water. So C10H14N2 aqueous reacting with water in a pure liquid form. Okay. And because this is acting as a base, what's going to happen is that part of this molecule, the nicotine molecule, actually the nitrogen, is going to go and take one of those protons from water, and because it's acting as a base. So what we get then is an extra hydrogen in our structure. And a positive charge because we've picked up an extra proton without its electron. And then since we've taken that proton off of water, we get OH minus. These are both aqueous. Okay? This here is the protonated base, so our goal is going to be to find the concentration of that. And protonated just means it has an extra proton on it. So let's, and since we've got a Kb value, that is a good clue to use a Rice table because this is an equilibrium, this is a weak base, so not all of those nicotine molecules are going to go and accept a proton. We need to know how many do. So we're going to set up a Rice table. There's our reaction. Okay, and initially we are told that we have 0.012 molar of this base. So I'm going to put that on the initial line. And we ignore the water because it's a pure liquid and it doesn't enter into the K expression. And then we're going to start with 0 of both of these species. As it reacts over time, we're going to use up some of these nicotine molecules, however many, it's minus X, and we're going to add some of the protonated base and some of the OH minus. Okay, and so if you take those initial and change rows and add them together to make the equilibrium row, you will find 0.012 molar minus X, and then X and X. Now at this stage, you should be thinking, am I able to use the small x assumption? Because you often are for this. And so the way to do that is to take the initial concentration and divide it by the K. And in this case, we have two significant figures for both the initial concentration and the K value, right? The sig figs come in here and the coefficients. And so we just need that initial concentration divided by the K to be greater than 100, because that means that those two values are far enough apart from each other that whatever difference there will be in using our small x assumption will not show up in our significant figures. So let's do that calculation. 0.012, I'm just checking for the small x assumption here, over 1.0 times 10 to the minus 6, and I should already be noticing, well, I'm taking 1.2 times 10 to the negative 2 and dividing it by a really small number, 1.0 times 10 to the negative 6. It probably will be the case that I can use the small x assumption. So that gives me 12,000. So that's definitely much greater than 100, which is the cutoff that we would have used because of the two sig figs. So remember that our cutoff is always 10 to the power of the number of sig figs. So since we have two sig figs, then it's 10 to the power of 2. That's our cutoff. It's much greater than that cutoff. So I can use the small x. So therefore, use small x assumption. Okay, so now let's go through this. So I am going to actually, the way that we use the small x assumption is I'm going to ignore that minus x in the equilibrium row, because that's going to make my calculations a lot easier. We're not going to have to use the quadratic equation. And let's write the expression for k, because we have a kb value. So that's x squared, because we have the two x's multiplied by each other in the products row, over simply 0.012 molar. We set that equal to 1.0 times 10 to the negative sixth, and we solve for x. Okay, so if we solve for x, then we will end up getting 1.1 times 10 to the negative 4. Okay, and so this equals our concentration of the protonated base up here. It equals the concentration of our OH minus right here. And then if we were to subtract this number from 0.012, we would get the concentration of the nicotine molecules left. And note that that it would still be within our sig figs. It would still be 0.012. So that's where the small x assumption, you know that it's working, because it's too small to even show up in the sig figs when you subtract it from the initial concentration. So then, okay, we know x. Now we need to know the pH of this, right? And so this x is not equal to the hydronium concentration, which is what we need in order to calculate the pH, but it is equal to the concentration of OH minus, okay? And so, so we can calculate the pOH. So pOH equals negative log of 1.1 times 10 to the minus 4 molar, okay? And that equals 3.96. Okay, so we know that this is basic because it has a low pOH, which would mean it would have a relatively high pH. And remember that all you do when you're transforming between pOH and pH is you're assuming that you're at 25 degrees Celsius. You can always make that assumption unless you're told otherwise, and in which case those two values add up to 14. So all we have to do is say pH equals 14. We'll give it 2 decimal places. That's the convention, minus 3.96. Okay, and so the pH is 10.04. Now that makes sense because we know that this nicotine is acting as a base. So you're going to have a relatively high pH, which is what we have. Okay, so that answers this question: what is the pH of the solution? What about percent protonated base? So if we have so we take the concentration of the ions that we get when the nicotine breaks up, and that is our 1.1 times 10 to the minus 4 molar. So this is the percent protonated base here, or this is not the percent. This is the concentration of our protonated base, which is C10H15 N2 plus, okay? And because we want a percentage of our original solution, we just simply divide that by our original concentration, which is 0.012 molar of C10H14 N2 initially. Because this is a percentage, we're going to multiply by 100. And when we do this, we get 0.92%. Okay, so not 92%, not even 1%, so close to 1%. And so that makes sense with what we found, which is that the x is so small, we can ignore it in our overall calculations. And because that x is small, that means that the majority of the nicotine stays nicotine, and only about 1 in every 100, little less than 1 in every 100 of those molecules goes and picks up a proton from water.